Welcome to the tutorial over 7.1, Graphing Exponential Functions. Your new vocabulary is exponential function, exponential growth, asymptote, growth factor, exponential decay, and decay factor. Your first key concept is parent function of exponential growth functions. So it's just showing you that this is what the parent function looks like. The type of graph is continuous and one-to-one. It's increasing as well. The domain is all real numbers. The range is all positive real numbers. You have an asymptote on the x-axis, which means that this line is always going to get really close to the x-axis, but it's never going to actually touch it. And then we have an intercept at 0, 1, and that is right here. So that's a y-intercept. Okay, example 1 wants us to graph y equals 4x and state the domain and range. We're going to use the exponential growth function, We're going to use that parent function from before so that we can get an idea of what this is going to look like. And actually, this question is supposed to be y equals 4 to the x power, not 4 times x. This thing messes up, sorry. So if we don't already know how to graph these, the first thing that we should always think of is drawing a table. So we're going to have our x values and our y values. So we're going to plug in some negative numbers and so that we can get the negative side of the graph, and then some positive so we can increase. So let's just say we're going to start with the negative 2. We'll do negative 1, 0, 1, and 2. If we raise 4 to the negative 2 power, that's going to give us a 1/16. You can put this into your calculator. When we do 4 raised to the negative 1 power, we get 1/4. 4 raised to the 0 power equals 1. 4 raised to the first power equals 4. And 4 raised to the second power equals 16. So that's how we get our table. So here's a cleaner look at the table, and it's a little bit more organized, but this is how you find it over here. So now what we're going to do is we're going to graph our points on a graph. So I'm just going to count by ones. So we'll say this is 1 and 2, negative 1, negative 2, and then of course our 0. So we're going to go to negative 2, and it's 1/16. So this is barely going to be above that line. Let's say that that's 1. Then we go to our negative 1, and that's going to be 1/4. So it's going to be a little bit closer up. At 0, we have 1. So we're going to put a point right here at 1. And then our 1 graphs or maps to 4. So we're going to go to 1, and then we're going to count up 4 spaces and put a dot there. And then our 2 goes to a 16, so it's going to be way up here somewhere. So once we graph that line, it's going to look something like this. So again, here's a cleaner version of the graph here. It looks a little bit better than mine does, but you can see how your asymptote gets really close to the line but never touches, and then the other side just takes off and goes increasingly very quickly. Alright, so our next key concept is going to be over transformations of exponential functions. So here you can see our model equation. We're going to say that h is equal to our horizontal translation. So anytime we have our exponent added or adding or subtracting a number, that's going to be our horizontal translation. So if h is positive, then it's going to move h units to the right. If h is negative, then we're going to move h units to the left. Okay, now our k stands for vertical translation. So our plus k on the end here, whatever k is, we're going to use that. We're going to go that many units up if it's positive, and whatever k is, we're going to go that many units down if it's a negative. Now, the a variable is going to affect orientation and shape. So, if we have a negative in front of our a, then that's going to flip our graph about the x-axis. So just like anything else, if we have a negative, then it's going to flip it across the x-axis. Now, if your a is greater than 1, so if it's greater than 1, then it is going to stretch vertically. If it's in between 0 and 1, meaning if a is a fraction, then the graph is compressed vertically. So if it's a whole number and it's greater than 1, then it's stretched. If it's a fraction, it's compressed. So example 2 wants us to graph the function y equals 3 to the x minus 2. And we're going to state the domain and range as well. So the first thing, like before, we're going to draw a table. We're going to have our x values and our y values. So I'm going to plug in -2, -1, 0, 1, and 2. So I'm going to put the -2 up here in my exponent. So 3 raised to the -2 power is going to equal 1/9. And then we're going to subtract 2 from that, which equals approximately -1.963. We will continue to enter in our next values of x through to get all of our answers, but for now I'm just going to insert this table so you can see how that works. Now we're going to plug in all these values to our graph and we'll draw the line. After you graph it, it should look something like this. Now our domain is going to cover all real numbers because it gets very negative. So now that we have our graph, we can determine what our domain and our range is. So if we look at our x values for our domain, we see that they go to -infinity on the left-hand side, and on the right-hand side, it gets closer and closer to the very right-hand side of the graph. So it's going up, so it's going to continuously head in that direction. So we know that our domain covers all real numbers, which we can write it as an R with a double line in the front, or we can just write out all real numbers. Now for our range, we're going to look at our y values, and we're going to see that right here is our horizontal asymptote. It approaches -2. So once you put that into your calculator, you'll see it a little bit better. So we'll say that our range, it's never going to touch -2, so it's going to be our y values such that y is going to be greater than, because my y values are increasing, but not equal to, because it's never going to touch the -2 line. And that is your domain and range right here. Example 2b, graph the function y equals 2 to the x minus 1. Then state the domain and range. So just like before, when we get a function and we need to graph it, we're going to go ahead and make a table. I'm just going to insert the table to save time. So you're going to plug in some negative and some positive values, or you can just put this equation into your calculator. And then we can go ahead and plug those points in on a graph and graph it. Okay, so here's our graph. We can see that there is going to be a horizontal asymptote somewhere out here, and then we can see that our x values are going to go all the way very, very negative and very, very positive. So we know that our domain again is going to be all in real numbers. So we would write it as x such that x equals all real numbers, and then we're going to look at our y's to figure out our range. And once you put this in your calculator, you'll be able to see easier that this is approaching 0. So our asymptote is at 0, so our line is never going to touch the 0. So our range is going to be our y values such that our y is greater than, but never going to be equal to 0, since our y values are increasing. Example 3 is a word problem. So it says, in 2006, there were 1,020,000,000 people worldwide using the internet. At that time, the number of users was growing by 19.5% annually. Draw a graph showing how the number of users would grow from 2006 to 2016 if the rate continued. So first, we're going to write an equation using A as our number of people. So we're going to say A equals, and we're going to make this 1,200,000,000,000 look a little bit better by just saying 1.020, and we'll say that this is in trillions. I'm sorry, I've been saying trillions, it's billions. So let me write that the right way. Sorry. Okay, now that we've got that figured out, and then we're going to say that our rate, our percentage here, our growing by, we're going to say that's R, and we're going to do it in a decimal form instead of as a percentage. So we're going to say our rate equals 0.195. So the equation that we use for exponential growth, we're going to put our A in front. So we're going to say y equals A times 1 plus our rate. raised to the amount of time that it's happening over. So we're going to say 1.020 times 1 plus 0.195, because that's our rate, and then we're going to raise it by however much time. So we're going from 2016 to 2006, or 2006 to 2016. So we're going to subtract those two, and we're going to see that we're doing it over a 10-year period. So we're going to put a 10 as our exponent up there. Now this will give us the exact number for that specific time period. But if we want to draw a graph, we need a variable, so we can just erase this 10 here and we can replace it with a t. That way we can draw a graph with that. So make sure you write all this down. I'm about to erase it. So now we can make a table of values to map out our graph, or we can just put this in our calculator. And if we do put it into the calculator, we're going to get something that looks along the lines of this. So we're starting at 2006, we're going up to 2016, and this shows our users in billions. So here we can see at 2016, we'd be around 6 billion users of the internet. Alright, so we have our second key concept here. It's parent functions of exponential decay functions. So before we have exponential growth, now we have exponential decay. So if you think about growth and decay, growth means that it's getting bigger and decay means it's getting smaller. So whenever you see a graph decreasing or a negative slope like this one here, you know that it's a decay function. Now the parent function is going to look like b raised to the x power, where b is a fraction. So we're going to have a fraction raised to the x. The type of graph here is, it's a continuous, it's one-to-one, and it's decreasing. The domain is always going to be all real numbers, and your range is going to be positive real numbers. We do have an asymptote along the x-axis, a horizontal asymptote, so that means here the graph is going to get really close, but it's never going to touch that. And we also have an intercept, a y-intercept at 0, 1, just like the exponential growth function had one at the same spot. So now let's look at an exponential decay function. We have y equals 1/5 raised to the x power. So what we're going to do is graph it, and we're going to state the domain and range. Now to graph, we'll do the same thing as we've been doing. We're going to create a table, of course. So here is our lovely looking table here. We use values of -3, -2, -1/2, 0, and on up. So once we get our graph, or once we get our points, we can plot those on our graph and we can draw the line to see what it looks like. Or you can just put it in your calculator and see it that way. Alright, so here's that graph. We can see that, like the key concept said, we do have an asymptote on the the x-axis here. We can also see that our range is all of these positive numbers up here all the way down to getting very close to 0. So we know that our range is going to be all y values such that y is greater than but not equal to, because it never touches 0. And then our domain, we can see, is going to be all real numbers. Now what we want to do is graph the function y equals -4 times 1/2 raised to the x minus 1 plus 2. Sorry about that, Belle. So we're going to state the domain and range. So if we look back to our very first key concept that we had, it's going to tell us what each one of these numbers that are added on here mean. So if we pick this apart and we look at all the extra things and take them off, we know that this function is going to be a representation of the graph 1/2 to the x power, but it's going to have a little bit of transformations added on there. So if we know that this is our original and then we have a -4 in front, we know that the graph is going to be reflected across the x-axis. We also know that this number out front, which if you look back to your notes equals a, we know that it's going to stretch vertically since it is greater than 1. We also see that our value here, h, is going to translate the graph 1 unit to the right. So even though there's a negative there, we do the opposite of that because it's backwards. So instead of going to the left 1 unit, we're going to go to the right 1 unit. Also, we have a k added on the end here. This is our k value. So that 2 is going to mean that the graph is translated up 2 units. Now that we know what's going on with our graph and we've picked apart each piece, we can now begin to graph it. So we can do a couple of different things. We can use our original equation up here that we found was being manipulated, and we could graph that and then apply all these transformations that we found. Or we can just plug this equation straight into the calculator and we can find that this is what our graph looks like on the x and y axis. Now by looking at the graph, we can tell that our domain is going to again be all real numbers. And then we can also see that our range is going to be all of our y values that are going to be less than 2, because our graph is a decay, so it's going downwards. It's coming, well, rather, the graph is coming up from being very negative, and it's getting really, really close to the 2, but it's never actually touching it. So that's why we do not have an equal sign under there. Our second word problem, example 5a, says the pressure of the atmosphere is about 14.7 pounds per inches squared at Earth's surface. It decreases by about 20% for each mile of altitude up to about 50 miles. Draw a graph and represent atmospheric pressure for altitude from 0 to 50 miles. So the first thing that we're going to do is we're going to identify our A and our R. So initially we know that the pressure of the atmosphere where we're starting out is 14.7, and we know that the rate of change is 20% for each mile. So our rate we're going to do in decimal form again, so percentage to decimal, 0.20%, or I'm sorry, rate is 0.20, which translates to 20%. And so we're going to insert that into our decay equation, which would be y equals a times 1 minus r to the t. So our growth function has a positive symbol here, but with our decay, since it's getting smaller, we're going to subtract here. Think of it that way. So now we're going to take all the values we just found and we're going to put them in. So we have y equals 14.7 times 1 minus 0.2, which gives us 0.8, raised to the t power. Now again, we can use a table to graph this, or we can just put it into our graphing calculator. So here we can see our graph representing atmospheric pressure for altitude. Here's those two labeled. We can see that it's a decreasing graph, so we know it's a decay, and it starts at 0 and it's going to go all the way up to 50 miles. But we can see that as we get higher, our asymptote gets closer and closer to 0. So it never touches, but it's going to be a very minuscule amount. Alright, so one more word problem. It says the pressure of the atmosphere is 14.7 pounds per inches squared, same as the last problem. It decreases by 20% for each mile of altitude up to about 50 miles. So what we're going to do in this question is estimate the atmospheric pressure at an altitude of 10. So we're going to keep our same equation from the previous question. So we're going to have y equals 14.7 times 0.80 raised to the t power. But we're given that we're going to be at an altitude of 10 miles, so we know that 10 miles have gone by. So what we're going to do is replace t with 10. So y equals 14.7 times 0.80 raised to the 10th power. And then we will use our calculator to approximate this answer to be about 1.58 pounds per inches squared. So the way that our answer will read, if we write it in a sentence, is the atmospheric pressure at an altitude of about 10 miles will be approximately 1.6 pounds per inches. And this concludes today's tutorial over 7.1, graphing exponential functions.